Hello, my dear students of Benguet State University. Welcome to our online class. I am your teacher, Jan Lasea.
Ladies and gentlemen, a blessed day to everyone. This is my ninth lecture in our subject IT 121, Platform Technologies. In my previous lecture, I explained the load and store architecture, the microprocessor without interlock pipeline stages or MIPS, the central processing unit or CPU, the von Neumann computer, and the machine cycle. Today we are going to learn the design principles for modern computers, parallelism, the Flint's taxonomy of computer architectures, pipelining, instruction level parallelism, and the 5-stage pipeline. The design principles for modern computers suggest a better and efficient design of the central processing unit or CPU. Number 1. All instructions are directly executed by hardware. All common instructions are directly executed by the hardware. They are not interpreted by micro instructions or micro program. Eliminating a level of interpretation provides high speed for most instruction. Micro instruction is a single instruction in a low-level computer program. Example, 10 instructions at 100 nanoseconds. Number 2. Maximize the rate at which instructions are issued. Modern computers resort to many tricks to maximize their performance, chief among which is trying to issue as many instructions per second as possible. After all, if you can issue 500 millions of instructions per second, or MIPS, you have built a 500 millions of instructions per second processor. No matter how long the instructions actually take to complete. This principle suggests that parallelism can play a major role in improving performance, since issuing large numbers of slow instruction in a short time interval is only possible if multiple instructions can execute at once. Number 3. Instructions should be easy to decode. A critical limit on the rate of issue of instructions is decoding individual instructions to determine what resources they need. Anything that can aid this process is useful. That includes making instructions regular, fixed length, with a small number of fields. The fewer different formats for instructions, the better. Number 4. Only loads and stores should reference memory. One of the simplest ways to break operations into separate steps is to require that operands for most instructions come from and return to registers. The operation of moving operands from memory into registers can be performed in separate instructions. Since access to memory can take a long time or slow, and the delay is unpredictable, these instructions can best be overlapped with other instructions if they do nothing but move operands between registers and memory. This observation means that only load and store commands or instructions should reference memory. Also, the less access to memory would improve the speed performance of the CPU. Number 5. Provide plenty of registers. Since accessing memory is relatively slow, many registers, at least 32, need to be provided so that once a word is fetched, it can be kept in a register until it is no longer needed. Running out of registers and having to flush them back to memory only to later reload them is undesirable and should be avoided as much as possible. The best way to accomplish this is to have enough registers. Also, registers are high-speed memory inside the CPU and are used as pre-fetch buffers. Parallelism. Parallelism is the act of performing several small subtasks at the same time in order to do more quickly a larger task. Parallelism is also called concurrency, synchronous, simultaneous, and multitasking. The types of parallelism that exist within a processor designs are usually categorized as being related to either data or instruction. That is, we typically want to operate either on several items of data at the same time using a single instruction, or execute several different instructions at the same time. The basic idea that is that a single processor should be composed of multiple processing elements, each of which operates in parallel and can potentially communicate with each other via some mechanism. Computer architects are constantly striving to improve performance of the machines they design. Making the chips run faster by increasing their clock speed, or also called overclocking, is one way. But for every new design, there is a limit to what is possible by brute force at that moment in history. Consequently, most computer architects look to parallelism, doing two or more things at once, as a way to get even more performance for a given clock speed. Flint's taxonomy. It is a classification of computer architectures proposed by Michael G. Flint in 1972. Let us learn the different classification of computer architectures according to Michael J. Flint. Number 1. Single instruction, single data. There is only one stream of instruction and one stream of data, ignoring coprocessors and additional processing elements or processing unit added to produce identical redundant computation. For example, to cope with errors, there can only be one useful processing element in such processor. Old Intel CPUs such as 8186, 8286, and 8386 are examples of single instruction, single data. The single instruction, single data classification is a poor in CPU performance because only one processing unit or processing element that performs single instruction with single data. Number 2 classification of computer architecture according to Michael Flint. Single instruction, multiple data. There is only one stream of instructions, but there are many streams of data. Thus, we can have many processing elements or processing unit, each executing the same instruction at a given point in time, but using different data in its case. Examples of single instruction, multiple data computers or processors include the Cray series of vector supercomputers and the graphics processing units or video cards that render 3D images or computer graphics within most modern graphics cards. The Intel CPUs such as the Core Duo, Quad Core, I-Core 3, I-Core 5, I-Core 7, and I-Core 9, together with the RISC and supercomputers, are examples of single instruction, multiple data. The single instruction, multiple data classification is the better in CPU performance because multiple processing unit or processors that perform single instruction with multiple data. For example, I-Core 5 has 5 cores of 5 or 5 CPUs or 5 processing units that allows 5 different softwares to be run simultaneously without slowing down. Number 3. Multiple instruction, single data. While multiple instruction, single data fills out the Flint's classification, it is difficult to envision. A single instruction stream is simpler than multiple instruction streams, but multiple instruction stream with multiple data streams are easier to imagine than multiple instruction with single data stream. This multiple instruction, single data, has few real-world application, and that's the reason why it is difficult to envision, and it is very rare. Number 4. Multiple instruction, single data. It is hard to justify the existence of multiple instruction, single data processors, in the sense that it is hard to see how such a device could compute useful results. What we are describing is a situation where we take a single data stream and operate on it using many different instruction streams. Examples of multiple instruction single data processors are rare, but application areas are typically those that require some form of duplicate computation. For example, a computer to forecast weather might run several simulation models on the same dataset and average the results to get a more reasonable result of predicting weather. Number 5. Multiple instruction, multiple data. There are many streams of instructions and many streams of data. Essentially, we have many processing elements or processing units or processors executing different instructions on different data at the same time. In a sense, this is the most general form of parallel processor. Examples include a cluster of workstations or distributed systems, where processing elements are physically separate computers connected by a network in order to collectively perform some task. In distributed computing, a problem is divided into many tasks. Each task is assigned and solved by one or more terminal or client computers simultaneously, which communicate with each other via message passing. Parallelism comes in two general forms: instruction-level parallelism and processor-level parallelism. In the former, instruction-level parallelism is exploited within individual instructions to get more instruction per second out of the machine. In the latter, referring to the processor-level parallelism, multiple CPUs work together on the same problem. Each has approach at its own merits. And here are examples of instruction-level parallelism, the 5-stage pipeline. Here is an example of processor-level parallelism. We have 4 CPU and 1 shared memory, and then they are communicated through a single bus. Instruction-level parallelism. Pipelining is an implementation technique whereby multiple instructions are overlapped in execution. The manufacturer of cars within the Ford Motor Company is a good example of pipelining. Ford Motor Company, under the direction of the owner, Henry Ford, used a system of continuous production lines to build automobiles. While one person was assembling the engine to car number 4 on car, another person could be attending to the bodywork on car number 2, while yet another person could be filling the wheels on car number 3. By around 1913, Henry Ford had his production line down to such a fine art that they were able to double the output of all their competitors, selling half of all automobiles purchased in the USA. Production or assembly lines in the context of manufacturing offer a neat analogy for the concept of pipelining in digital logic circuits. The idea of a production line is for the end result to be produced as the combination of a number of basic steps. However, instead of performing the steps sequentially, each worker within the production line can be dedicated to one stage, mastering it to an extent which meant their output is higher than normal. Secondly, it allows for division of labor in the sense that one can scale the level of output closely within the number of workers. Roughly speaking, The more workers one has, the greater the output. This is largely because of the fact that the workers in a production line can all be working effectively at the same time or simultaneously. In particular, one worker is not idle while waiting for another to finish or for tools to become available. The pipelining in car assembly results to first car assembled in 4 hours. Thereafter, 1 car per hour. 21 cars on first day. Thereafter, 24 cars per day. 717 cars per month and 88,637 cars per year. And that is the effective throughput or output of using pipelining in car assembly line. Pipelining become a de facto standard in manufacturing because it increases the production. Thus, most manufacturers use pipelining, such as makers of cupcakes, soap production, beverage manufacturing, and automobiles assembly. Some manufacturers use moving conveyor belt in their production line. It has been known for years that the actual fetching of instruction from memory is a major bottleneck, or it is very slow in instruction execution speed. To alleviate this problem, computers going back at least as far as the IBM Stretch computer in 1959 have had the ability to fetch instruction from memory in advance, so they would be there when they were needed. These instructions were stored in a set of registers called the prefetch buffer. This way, when an instruction was needed, it could usually be taken from the prefetch buffer rather than waiting for memory read to complete. In effect, prefetching divides instruction execution up into 2 parts, fetching and actual execution. The concept of a pipeline carries this strategy much further. Instead of dividing instruction execution into only 2 parts, it is often divided into many parts, each one handled by a dedicated piece of hardware, all of which can run in parallel. I introduce to you the 5-stage pipeline. In the instruction level parallelism, it gets and processes more instruction per second out of the machine. The 5-stage pipeline is an instruction level parallelism. The 5-stage pipeline is a pipeline with 5 units, also called stages. S1 is called stage 1, S2 is stage number 2, S3 stage number 3, S4 stage number 4, and S5 stage number 5. Stage number 1 fetches the instruction from memory and places it in a buffer until it is needed. Stage number 2 decodes the instruction, determining its type and what operands it needs. Stage number 3 locates and fetches the operands either from registers or from memory. Stage number 4 actually does the work of carrying out the instruction, typically by running the operands through the data path. And stage number 5 writes the result back to the proper register. The figure below, we see how the pipeline operates as a function of time during clock cycle number 1. Stage 1 is working on instruction number 1, fetching it from memory, while stages S2, S3, 4, and 5 are idle and are waiting for a task on clock cycle number 1. During clock cycle number 2, stage 2 decodes the instruction number 1, while stage number 1, S1, fetches the next instruction, instruction number 2. During the cycle number 3, stage S3 fetches the operands for instruction number 1, while stage number 2 decodes instruction number 2, and stage S1 fetches the next instruction, instruction number 3. During the cycle number 4, stage number 4 executes instruction number 1, which was passed by stage number 3, while stage S3 fetches operands for instruction number 2, while stage number 2 decodes instruction number 3, and stage S1 or number 1 fetches the next instruction number 4. Finally, during cycle number 5, stage S5 writes the result of instruction number 1 back, while other stages work on their following instruction. At cycle 5 and onwards, all the 5 stages are busy doing their assigned tasks. This creates parallelism, meaning many instructions are being worked out by the 5 stages simultaneously and continuously without idle or rest or delay. Another way to understand the better performance of pipelining or the 5-stage pipeline is to take a look on the comparison between non-pipeline and pipeline. In a non-pipeline, one instruction is being processed by a stage at a time. Thus, it makes the other stages idle and it completes one instruction every 4 clock cycles. On the other hand, a pipeline, more than one instructions are being processed by more than one stage simultaneously. Thus, less number of stages is idle and it completes 2 instructions every 5 clock cycles. Another way to understand the better performance of pipelining or the 5-stage pipeline is to take a look on the comparison between non-pipeline and pipeline. In a non-pipeline, one instruction is being processed by a stage at a time. Thus, it makes the other stages to be idle and it completes one instruction every 4 clock cycles. On the other hand, a pipeline, more than one instruction is being processed by more than one stage simultaneously. Thus, less number of stages will be idle and it completes 2 instructions every 5 clock cycles. Getting back to our 5-stage pipeline, suppose that the cycle time of this machine is 2 nanoseconds. Then it takes 10 nanoseconds for an instruction to progress all the way through the 5-stage pipeline. At first glance, with an instruction taking 10 nanoseconds, it might appear that the machine can run at 100 MIPS or millions of instructions per second. But in fact, it does much better than this. At every 2 nanoseconds, one new instruction is completed, so the actual rate of processing is 500 millions of instructions, not 100 millions of instructions, because 100 millions of instructions per second multiplied by 5 stages is equal to 500 millions of instructions per second. Pipelining allows a trade-off between latency, how long it takes to execute an instruction, and processor bandwidth, how many millions of instructions per second the CPU has. With a cycle time of t nanosecond and n stages in the pipeline, the latency is computed by multiplying the n stages multiplied by the cycle time, and the bandwidth is computed by 1000 divided by t millions of instructions per second. Latency of a pipeline is the total elapsed before a given input is operated on to produce an output. This is simply the sum of the times taken by each pipeline stage. The bandwidth or throughput of a pipeline is the rate at which new inputs can be offered to the pipelines, outputs produced by the pipeline. This is typically limited by the stage that takes the longest time, since this stage will dictate how fast the pipeline can be advanced. I posted your 9th assignment in our Google Classroom. Please answer and accomplish it.
That ends our topic for today. I hope you have learned in my class. Thank you for watching. Carry on until tomorrow. God bless us.